And thank you for your words. Thank you everyone for coming, and thank you for people online for joining. I'm really excited to be here. So I've been studying the problem of land change and wild habitat change for the past 5 years here at UW Madison. And today I'm going to show you my work and how remote sensing has helped me answer some ecological questions about important ecological questions about wild habitats and future of wild animals and us as humans on Earth. Specifically, I'm going to look at how land cover has changed in the past half a century within a politically and biologically diverse area, and how it has affected the habitats of wild mammals. The way Earth's land cover on Earth looks like today strongly depends on the decisions and choices of our previous generations, and our current choices will likely have similar legacies in future. While land use on Earth has a long history of many centuries, it has accelerated over the past few decades due to technological advancements. Especially large changes happened after the mid-20th century, which is when the World War II happened and was followed by the baby boom, and that generation grew to be adults in 1960s. So all of these events prompted high food demand, high need in food production, and which in turn prompted also green revolution, meaning major agricultural advancement. Here I wanted to show you that the human population has been growing for a very long time, for centuries and millennia, but the magnitude has been completely different in the past half a century. So the Green Revolution, major agricultural advancements, this revolution actually increased crop yields and increased food production, which was actually very good and successful in mitigating hunger globally, but it also had strong effect on environmental degradation, contribution to environmental degradation. Cropland expansion in unsuitable areas and conversion of grasslands into pastures, they all could lead to changing biophysical characteristics of soils and to soil erosion and soil degradation, and also environmental problems in rivers, in waters, in general, loss of natural ecosystems. However, most habitat and land change assessments start after the release of freely available 30-meter Landsat thematic mapper data, so in the 1980s, or when the commercial high-resolution satellites were launched in the 2000s. But these studies dating back to the 1980s are missing the important changes that happened in the middle of past century. Meanwhile, in that era, the United States and the Soviet Union, the two largest powers of the 20th century, were in the middle of the Cold War. And that Cold War also fueled the space race between them. And one of the successful outcomes of that space race was the launch of Corona satellite series in 1959. They were mainly aimed at capturing Soviet military sites and missile launch sites, but they also captured the state of the environment at that time. Corona was the code name of the mission, and it owes its name to the Slavic word, to the word of Slavic origin, corona, which means a crown. And the reasoning for that was that it was supposed to be above the Soviet Union, so it'd be like Corona of Soviet Union. Same reason for the naming of coronavirus. The shape of it looks like a crown. And as I just found out, also the beer Corona. The process of bringing Corona data back to Earth was actually very fascinating. So when the capsule that would detach of the satellite, it would come close to the Earth. And as it approaches, the satellite would open up, and the pilots of the United States Air Force, called Corona star catchers, would go on a capsule hunt and capture them. It was called mid-air recovery of the capsules. Here's me being very happy to see the Corona in DC. And this is exactly that same capsule that they were capturing in the air. And here it is also very small in red. While the Soviet Union and its surroundings were the main focus of these Corona satellites, they also captured extensive imagery across all continents. When in the 1990s, the Soviet Union collapsed and there was no more need to keep this mission a secret, in 1995, President Clinton declassified this imagery. They released to be used for scientifically or environmentally important purposes, captured specifically by these satellites. Although the Corona data was captured over 50 years ago, it consists of panchromatic imagery of incredibly high resolution of 1.5 to 3 meters. And I wanted to show you here how detailed they are. So for example, we can see, this is exactly like we're looking at it on Google Earth, right? So problems here, where can you see very well where the world is running, the urban areas are very, very detailed. So my overarching goal for my dissertation was to advance the field of remote sensing, long-term land change science, and habitat modeling. And I mainly had 3 focus areas, which was remote sensing, land cover, and biodiversity and conservation. So for remote sensing, I wanted to develop an approach to map the historical spy satellites, the land cover using the historical spy satellites. And then for the second question, I wanted to evaluate long-term land use changes using this data, especially through the large-scale sociopolitical events such as the collapse of the Soviet Union and the subsequent wars. And also the biodiversity and conservation focus to incorporate Corona data into assessing changes in habitats and also evaluating how successful were the protected areas in conserving and restoring them. Excuse me. To answer all these questions, my study area was the Caucasus ecoregion. It's located at the brink of Europe and Asia, and more exactly between the Black Sea on the west and Caspian Sea on the east. My study area covers approximately 240,000 square kilometers in the Caucasus. This is about 1.5 size of Wisconsin, but it's highly diverse in elevation, ranging from -27 to about 5,600 meters above the sea level. It also has high variability in terms of precipitation, climate, biodiversity, and ecosystems, and it plays an important role for migratory and resident species. Unfortunately, the Caucasus is considered as one of the 36 global biodiversity hotspots with many ecosystems and species of conservation concern. For many centuries, cropland cultivation and livestock production has been an important part of the local economy, but being strategically located between Europe and Asia, the Caucasus has always been part of every large empire that has existed in the region. So the Ottoman Empire in the 1600s, which is mainly current-day Turkey, the Persian Empire, which was in 1800s, and it's currently mainly area of Iran. The Russian Empire, which was in late 19th century and early 20th century. But for most of the 20th century, the Caucasus was ruled by the Soviet Union, and it experienced land use initiatives by the Soviet government. And also it has experienced the effects of its collapse and the subsequent wars, and also the policies that were introduced by the new governments of the new post-Soviet countries that emerged in the area. For all its socio-political events that it experienced and its diversity, Caucasus is an ideal location to study the land use changes and their effects on wild habitats, and also its diversity in terms of elevation, climate, and biodiversity. And it all means that the new approaches that I will develop here will be applicable in many other parts of the earth. Despite the high potential of corona data, it has, and also despite being declassified for almost 3 decades now, there is only a limited number of studies involving corona data. The main for this could be partly that it's not widely known, but also could be partly that it's not as easy to process as the current day multispectral satellite imagery. And so the objective for my first research question was to develop an approach to map the land cover using corona data. Here I wanted to show you the previous studies that have been conducted using corona data. And as we can see here, most of the studies are either limited in terms of the study area geographically, are either limited geographically. So they cover a small study area, but maybe they include several land cover classes, but they cover only a very small study area, like 25 meters along the x-axis. Or they included larger area, but they only captured one land cover class. So we're missing studies in this section of the graph here that would capture a larger area and a wider variety of land cover classes. The corona images are actually stored in the archives of the USGS EROS in printed versions. So when we order the imagery, they scan them and send us basically black and white image strips. Excuse me. I don't know how professors talk for so long in classes. So since we receive just black and white image strips, the first step that we need to do is to apply a auto-rectification process. And specifically for corona, this process was described by Mihai and performed by Mihai for this project that I'm describing. Thank you, Mihai. And so we stitched together 59 corona film strips that are for forward-facing and backward-facing corona cameras. And those 2 cameras were installed initially to be able to capture the stereographic view of the Earth. The first challenge that I faced when I received this corona imagery was and it was high-resolution imagery. The problem was how computationally expensive it is. In fact, it took me about 4 or 5 hours to segment only this image chunk, which only covers a small portion of my study area for this question. So I focused on this corona image from October 1964, covering mainly south of Russia, large part of Georgia, Armenia, northeastern Turkey, and a little bit of Azerbaijan. So my study area was about 160,000 square kilometers, and it ranged in elevations and in illumination conditions. The area of one image strip that you see highlighted here in yellow is approximately equals to the area of one Landsat tile, but with much higher spatial resolution, hence high computational expensive processing. Then at the start of my PhD here, I discovered this amazing platform called Google Earth Engines. I used it for its cloud computing capabilities, and I compressed and imported corona images to GE, and then I performed classifications within GE. So first, I tried the pixel-based classification. I combined first order and second order texture metrics and the elevation data to obtain the land cover maps. And for object-oriented approach, the process was pretty much the same, except that I also applied segmentation algorithm and generated the segments within the imagery, which I also applied. So here you can see their geometry characteristics in classification. I should also mention that I used random forest for both classifications, and my classifications are for the full suite of land cover classes. The results were overall good, but they were better for object-oriented approach. And also the higher numbers that you see here are in both approaches are when we incorporated the digital elevation data, so terrain data. Looking at the resulting maps, let's zoom into this red area here. It looks like none of the pixel-based approaches worked very well out of those that I've tried. So I do not recommend pixel-based classification for corona based on my results. But object-based, on the other side, was more successful, especially when including the object geometry information, such as area, shape, as we saw in the previous slide. So for future classifications, to achieve the best results, I would recommend combining texture metrics, object geometry metrics, and the digital elevation data to achieve the best results. Revisiting the first question, here I present a novel workflow for 2.5-meter high-resolution satellite imagery within a large area of 160,000 square kilometers, and for historical mapping for 1960s. This workflow is the result of my research of refining of parameters for feature selection for object-based and pixel-based, and also detecting the limitations and benefits of each of these approaches. And I built a set of codes on cloud-based processing platform, Google Earth Engine, and I suggest that with only slight adjustments of segmentation parameters, this workflow can be easily adapted to any other areas across the Earth where the corona imagery or any other aerial historical imagery with stereographic view is available. Moving on to the next question. Assessments of land change are strongly affected by the chosen baseline, which is usually the launch of Landsat TM data in 1980s. But global events of mid-20th century usually leave a long-lasting impact on current-day land use. And so corona data provides an opportunity to revisit the period when these global changes have occurred. So for this research question, I was aiming to quantify the long-term changes by applying the methods that I developed for the previous question, but to a larger area now. And what made this study area especially interesting were the socio-political events that it has experienced, and in the 60s and also afterwards. So I extend the study area to about 240,000 square kilometers, and also produce land cover maps for a full suite of land cover classes. Here you can see the numbers above each corona image, and they correspond to those in this table on the right side. Each image belongs to the different year. So the land cover that I obtained belongs to years 1964 and 65. Also on the right side of the table, you can see the results of auto rectification, which shows a successful, highly accurate results. Thank you, Mihai. For this research question, I used about 200 image film strips, performed rectifications, and object-oriented land cover classification. And then I compared corona maps to the Landsat-based maps that were developed by former lab mate Johanna Buchner. I applied the post-classification comparison to obtain the maps for Soviet era changes, the change maps to depict Soviet era changes, so compare 65 and 1987, post-Soviet changes, 87 to 2015, and next 50-year, overall 50-year changes before 65 to 2015. So here are the resulting 3 change maps for that, for each era, for each change time period. I assessed the area-weighted accuracy for each stable and change class based on the best practices described by Pontus Olofsson. And I also want to thank Neda Kasrai for collecting independent validation data for these maps. So just to show you a couple of examples, if we zoom here in Georgia, we can see the importance of corona data. So if we only look at changes from 1987 to 2015, we see a lot of brown, which is totally lost, right? So if we only look at post-Landsat data, we only see Scotland loss. We see how much Scotland has been lost after the collapse. But if we add the 1965 data to it, then we can actually see that they didn't use the Scotland, they were new Scotland. So the Scotlands that were later abandoned were actually the new Scotland. So it can help us uncover the unknown reasons for some of the land change processes. And specifically in this area, maybe the reason for these programs were to be established was to just government subsidies, and maybe it was hard to reach for machinery or general unsuitable areas, so it wouldn't be flawed if not for the government subsidies in the first place. While other areas where the cropland was that were more suitable for croplands, for example here, they were plowed before the 1960s and remained plowed in the Soviet era and after its collapse. And then another example here from the south of Azerbaijan, we see that the new center pivot agriculture was established after the Soviet collapse. Actually, it's more recent, which we also were able to capture here. So light green is the stable grassland, which then cropland gain, which is bright pink, takes over in the post-Soviet era, and we capture it in both change maps. Overall, I found that forests were lost during the Soviet era by 6%, and then they were gained actually after the Soviet collapse, so by 5%. So the importance again of corona here, similar to the maps that we saw, is that if we only look at post-Landsat era, then we see forest gain, but adding the 1965 baseline to it, we can also avoid the wrong impressions that all the forests have been gained, but rather see that the forests have been lost, which were later kind of recovering. The most widespread changes from 1965 to 2015 were grassland and cropland. So we observed continuous grassland gain by 11% overall, and cropland loss by 18% overall. But the magnitude of these changes differed between the different eras. So first, the cropland loss, grassland gain occurred by 4% and then 7% in the post-Soviet era. But cropland loss was only 3% in the Soviet era and 16% after the Soviet collapse. And we see the difference in the magnitude of these changes. And the abandonment rates were overall high, so we can see the like 16% post-Soviet abandonment of croplands. But compared to other post-Soviet countries or Eastern European countries, these numbers are relatively low. And the reason for this might be that the Caucasus there are many lowlands areas that were suitable for agriculture, and agriculture has been there for a long time, and it shows how incredibly stable croplands are in the Caucasus region. If we look at overall changes, the classes are overall stable, but we can see that there have been changes, a lot of changes between the classes. So they are now in different places if we compare them to the 1960s. To conclude, my analysis of the Caucasus demonstrates the possibility of applying corona data to change analysis, and it helps extend the time series further into the past, more exactly to the 1960s, by 2 decades before or beyond when the land change maps were, or land cover was mapped for large areas before. I combined multi-resolution satellite imagery such as Corona and Landsat to detect 50 years of land cover changes and emphasize the importance of Corona data for regions with substantial changes during that time frame. For my last research question, I incorporated the land cover maps that I developed previously to model and to project species habitats. My objectives were to assess wild ungulate habitat changes and also to evaluate how successful were the protected areas in saving and restoring these habitats. Human activities causing habitat loss and global climate change present a major threat to biodiversity, especially in hotspots. And that's why it's important to find out how much habitat has already been lost. Similar to land change studies, most studies in habitat changes only include the era after the 1980s, but by then much habitat has already been lost. This is a great example of shifting baseline syndrome, which means that limited or missing information of past conditions result in gradual change of our understanding of natural conditions. So, for example, in this photo, we can see that all these fishermen are very happy for their catch. In 1985, they're very happy for the fish that they caught, but would they be happy if they saw the fish that their older generation caught 20 or 30 years ago? With that in mind, for my last research question, I wanted to incorporate the 1960s land cover maps and try and extend the baseline of large mammal species habitat availability further back in time. This is especially important for large wild mammals because their lifespans are long, but their reproduction rates are low. And so it can take decades to accurately assess changes in their habitats, which can also lead to extinction depths. Unfortunately, species extinctions occur generations after the fragmentation has occurred, so they represent a debt, a future ecological cost of current habitat destruction. And so understanding the past conditions can help us avoid such debts in the future. Azerbaijan is a core part of the Caucasus biodiversity hotspot. It's very diverse in fauna. It has over 400 bird species and in general over 700 animal species. I also wanted to revisit the area changes here, specifically for Azerbaijan. We can see that the forests have been lost quite a lot after the 1960s, right? So if we're comparing for this, actually comparing 1965 and then 2003 era, we have the green rectangles have decreased quite a bit. And also, I want to bring your attention to the plasma problems here, where they look relatively stable with a little bit less problem currently, but there have been quite large changes between exchanges between these two classes. So in this chapter, I wanted to focus on the area of Azerbaijan and looking at the changes that have happened there. I wanted to see how those changes have affected the habitats of wild mammals. And so the study area includes the entire area of Azerbaijan and 25-kilometer buffer around it, because we wanted to account for environmental factors that are important for species, but they are outside of political borders. Here on the right side, you can also see the actual study area that was for our change maps, and the reason for this was the corona data availability. So our study area, basically corona data covers this area, with South covering some of the parts of Azerbaijan. So the study area for this question was about 90,000 square kilometers. I combined Corona and Sentinel data, actually land cover data, to develop ensemble models in R and to hindcast the wild mammals distributions back by 55 years. My species of interest were bezoar goat, chamois, golden gazelle, mouflon, red deer, roe deer, and East Caucasian tour. They are all, so here's my presence data that I used for this analysis. All the species are red listed except for two, and they are all in wild ungulates that exist in Azerbaijan, except for very widely spread wild boar and also newly reintroduced European bison. So I used that presence data to model the species distributions. I incorporated environmental variables such as land cover, climate, terrain data, and the proximity information, and built the ensemble models. The models that I built were based on current presence data and current, so 2021 climate variables, and then I applied that data to model to project species current probabilities of presence of 2021 and 1965. So I time tested the models built on current data to the 1965 environmental variables. The models that I built, they based on the true skill statistic, area under curves, and state and specificity. For most species, they are highly accurate. And so here I want to show you the second part of the graph too in more detail. So when I get the continuous map of species probabilities of presence, so for example, red here is showing higher chance of species presence in that location. We applied, we converted them to categorical maps by applying this rule. So all areas that had more than 55% chance of species being present there were now categorized as highly suitable. So here it is, and then 30 to 55 as moderately suitable, 10 to 30 as least suitable, and 0 to 10 as non-habitat. So these maps here are, for example, for tour species, just as an example here. And so we can see that the mountainous areas here are highly suitable for them, and the least suitable areas, they are all quite densely working in one greater conflict and less conflict. And then we compare this to categorical maps to detect changes between habitats of wild animals. I should also mention that the procedure was the same for all species, and I used the only difference were the environmental variables that I used for each species based on what was important for them specifically and based on the correlation between those variables. I summarized the results based on the world biomes introduced by Olson. And so the two large main biomes that were within our study area were Azerbaijan shrub, desert, and steppe in red, and the green Caucasus mixed forests. And so I divided the species into mountain species and the lowland species, with gazelle being our only lowland species and all others mountain species. Let's look at changes in their habitats here. So, for example, this is red deer. So we expect more their habitat to focus on mixed forest, which was the mountain, and less in the lowlands. And so here we can see that the non-habitats have increased since 2021. But all suitable categories have decreased in this time frame. And so, actually, I found that for most of mountain species, the habitat has unfortunately been lost since 1965. And possibly the reason was the forest loss that we observed in changes in Azerbaijan specifically. And it often occurred in the mountains too. In lowlands, though, interestingly, the habitats shifted in location, which may be due to abandonment of existing and establishment of new croplands in lowlands of Azerbaijan. In addition, I also obtained the borders of protected areas from the World Database of Protected Areas. And here on the map, you can see the in blue, the strictly protected areas, so reserves and national parks, and in blue, as I use in categories 1 and 2. And also not so strictly protected areas, all other protected areas, I think that was 3 to 6, such as sanctuaries, for example. So this graph is for strictly protected areas specifically. I think that is 1 and 2, as you can see. And I wanted to bring your attention to this graph because it shows that they were actually highly successful. For example, I want to show you an example here. We see the for raw deer, the habitats, especially the highly suitable habitats, have increased in all protected areas. And the way I divided them is both the protected areas that were established before the 1960s, 70s, the protected areas that were established still in the Soviet era, but after the 1960s. 70s, and the ones that were established after the Soviet collapse. So if we look at all of the changes, we see that the strictly protected areas were successful, but also it looks like the protected areas that were established after the Soviet collapse were more successful. So this can confuse us because they are younger or newer protected areas. But the reality is that for older protected areas, we do not see the state of habitat in that the area before they were established. And that's why for the newer ones, we do see what it was like before they were protected. And so we see a larger magnitude of changes in habitats, especially highly suitable habitats. And also it takes time for habitats to recover. So there is a time lag between when the area was established and when the habitats are actually recovered. So here I wanted to give you an example of a national park in Azerbaijan, which was established actually as a reserve in 1929. It's a little bit smaller area, so, and they, in all the reports that I read from 1950s, they reintroduced red deer in this reserve too, because they were gone, like, extinct from that area specifically. So as we can see based on our maps, that area actually shows it as least suitable. Still some suitable habitat, but least suitable. But as time passed with the existence of that specific area, they will see the improvement in habitats. We see more highly suitable habitat. And actually, based on current reports, these species are thriving in this protected area. So revisiting this question, the Corona spy satellites allowed me to extend the understanding of past habitat conditions to the 1960s and thus reduce the shifting baseline syndrome. My results highlight the success of protected areas in preserving habitats of wild mammals, and they inform the current ongoing plans to extend existing or create new protected areas in the region. Combining the historical and current data allowed me to evaluate the relationship between human activities and wild habitats. And so understanding these relationships can help us construct better conservation strategies and policies for land use, land management. Overall, in my work, I present methodological and scientific advancements, and I develop results important for land management and conservation. Scientifically, my dissertation contributes to global land change and environmental change sciences. I advance the field, understanding of landscape dynamics and habitat changes, particularly in regions with diverse history of land changes and political, complex historical trajectories. I'm sorry. By quantifying the long-term land cover trends in the former Soviet states, I was able to uncover how past land use decisions affect current-day land cover. And also by revisiting a period in the mid-20th century when the global events took place, my results uncover important historical patterns of land cover changes. From a methodological point of view, my research advances remote sensing by applying and optimizing approaches for processing high-resolution satellite imagery, specifically for corona satellite imagery, but can also be applied to other historical aerial imagery with stereographic vision. I present a novel workflow for corona spy satellites to map for the first time large area land cover for broad land cover types. From a management perspective, my work has implications both globally and in the Caucasus. For the Caucasus, a major biodiversity hotspot, my work provides an important foundation for cross-border conservation and management. It also informs the current and ongoing plans for creating new and expanding existing protected areas. The results of my dissertation will be used by the local and international organizations. So specifically, the Ministry of Ecology of Azerbaijan and Ministry of Agriculture will apply the results of my study in their work, and also the international organizations such as WWF Caucasus and WWF Azerbaijan. Globally, the ability to identify and analyze historical land cover helps provide informed decision-making in land use planning. And also my work provides important basis for the 1960s and helps apply that data to present-day land use management. It can potentially increase the ecosystem resilience against ongoing anthropogenic impacts. And also, I present here ways to extend or actually reduce the baseline of reduce the shifting baseline syndrome and potentially prevent species extinction. You have now seen this image a few times in this slide. This is actually in this presentation, sorry. This is actually the area where I'm from, where my parents are from. It's in Azerbaijan. And the Caucasus is very close, is a region very close to my heart. I have been very lucky to work in conservation there and in helping restore habitats and populations of local wild mammals. And there are two people that especially inspired me and guided me for that entire time, which is Elshad Askerov and Nugzar, and I'm very and I'm very grateful to both of them. I also want to thank my committee. Thank you, my lab mates. Thank you, my friends all around the world. And most importantly, thank you to my family. And thank you all for coming and listening to me.
Any questions about it?
Thank you for the question. Great question. So Corona data is actually kind of dramatic. So it's like black and white image that you see. It's very high resolution, so you can differentiate the features quite well. But it's time for nice image. The benefit that it has is two images specifically. So for stereographic view, they requires one with front facing camera and one with backward facing camera. So we could combine both images to maximize what we can get. Ensemble modeling. So this is actually something that I've looked into, ensemble modeling versus model averaging. They are not the same because model averaging is when you can develop models from completely different data sets, from completely different settings, parameters, and then average the models based on that. Ensemble model on the other side is you're using the same data set, same environmental variables, and you're just the only difference is the algorithm. So you build the models for each algorithm based on each algorithm, and then you average the results of those algorithms for ensemble. And the ensemble we can get different ways to calculate it. And the one that I used specifically here was weighted average, which is I weighted in the final formula that I used. I weighted each model based on how well each of the algorithms did, each of the models did. So, for example, random forest did best, and JLM did not so good. So random forest was weighted higher when averaging all these models together. Thank you.
I'm sorry, how did you categorize candidates from not suitable, somewhat suitable, very suitable?
Can you repeat the question for the microphone?
Sure. Yeah, so the question Jenny asked was how we categorized the continuous maps into categorical maps, right? Check, 1 second, please. So, yeah, for that we used expert knowledge mainly. So we looked at each map in detail, and we selected the thresholds, like each threshold. For example, to decide on the threshold for highly suitable habitat, we looked at 50, 51, 52, 60, between 50 and 60. And then, yes, and then we chose 55 as the best one that shows, so for 2021, it matches current distributions of species well. So we make sure that it at least includes, so it's like omission and commission errors, right? So we wanted to make sure that all habitats where they exist now are included in the highly suitable habitats. Yeah. Yeah. Yes. Yeah, good question. So the field data is yes, presence only. It was collected by local conservationists and mainly people who work in protected areas, and so but beyond them as well. So yes, it was visual observations, And for some of the species, like for gazelle, for example, we had also color data. The second question we had, I'm sorry. What's that one? Yeah, I forgot to repeat the question. Oh yeah. The temporal frequency is actually the data that I use for presence is from different years. So they start actually from early 2000s, but to make sure that they capture the habitats where they exist now, I went through each point and I made sure that the area where they exist, or actually where the point is, the habit, or actually the land cover hasn't changed there. So for example, if it was in the forest and it's still in the forest, then I kind of went on Google Earth and then looked back to 2000s whenever data was available, or Landsat imagery. And then I also used Johanna's maps to extract the land cover for each time step that she has for every 5 years. And so I made sure that the land cover hasn't changed. So it was deep forest and still deep forest. If it was at the edge, then I tried to eliminate those points where it could affect the habitat specifically. Thank you.
An online question I read quick from Catalina Montiano, a great piece of work. She's asking, well, the 1960s are great, but are some things happening before then? And so what are other data sources that could be used to go and changes, extend the timeline even further back? And you don't have to repeat that one since I'm forced to do.
Thank you, Katarina. Great question. So, for the time, so unfortunately, Corona is the only satellite that we have available for that time period. Actually, there were several launched, but Corona is the earliest that we have successful imagery for. But also, there are aerial photographs with stereographic or vision that could be used. And also, if we specifically want to study the land use changes, then we can also use the topographic maps or historical reports that were produced before the 1960s as well. And I can direct you to the studies that have done that.
Great talk, thanks a lot. Really exciting work. I was wondering how important the climatic variables were in the models and how climate has changed in Europe, if at all.
Yeah, great question. So Maurel is asking about the climate variables, whether they were important and whether climate has changed in the area at all. So in fact, from my baseline when I was born, if I compare like from my own experience, the climate has changed in the area. I remember when I was a kid, we had a lot of snow, now we don't. But looking at the satellite data specifically, when I look, for example, at 60s climate variables and at current, we see quite a bit of change there, which also had its effect on our maps, final maps. For specifically climate variables were important for gazelle species. For most species, it was land cover, or some of them it was distance to urban areas, for example, too. But for gazelle, the most important was climate variable, and especially temperature, I believe, is the most important. Yeah, thank you.